see.
Yeah, it's kind of a subjective thing. We'll go through it. My name's Leah Klein. CJ and I work for HNTB in Bellevue, Washington. Yeah. So this commute is kind of a big deal. People really don't like it. Recently, it's been in the news, and the Seattle Times labeled it the worst commute in the nation. So it's kind of scary, but also cool to see your project on the news, because it means people are paying attention. Yeah, basically, Everett is a larger city north of Seattle, and it's in Snohomish County, and an estimated 125,000 people commute between Snohomish County and King County, where Seattle is, every single day. So that's about 16% of the population of the whole county is commuting this corridor and then back every day. So yeah, it can take upwards of 90 minutes to get there during the peak hour in the PM. So yeah, it is a hot mess. So the reason it's technically the worst commute in the nation is because in 2017, the INRIC's scorecard determined that people in this segment spend 28% of their time in gridlock. So for a 24-mile segment, that's kind of a lot. So yeah, worse than New York City apparently in terms of gridlock, percent of time spent in gridlock. So that's where we come in. Our project was evaluating a 4-mile segment of I-5, but our Vissim model actually extended 8 miles further than that, so for a total of 12 miles, which is a very long Vissim model. Yeah, we were evaluating some different alternatives, different years, 2018, 2022, and 2040. Getting our forecast data from the Snohomish County Travel Demand Model. Yeah, basically WashDOT wanted us to look at adding some managed lanes, HOV lanes, general purpose lanes to this segment where they were completing a new interchange up at SR 529. So these are the 5 alternatives, build alternatives that we looked at. You can see up at the top there's 2 new interchange ramps to complete the SR 529 interchange. And we looked at a variety of different lane combinations, including adding no lanes at all. But yeah, we have peak use shoulder lanes, HOV lanes of different lengths, coming from US 2 all the way up to the new interchange. So CJ is going to talk about how it turned out and how we calibrated our model.
Yeah. Thanks, Leah. Let's just go to this next slide. So I'd say this model, as Leah mentioned, was 12 miles of I-5, and it really included a lot of different elements of Vissim. So we had freeway traffic, we had arterials, traffic signals, we had pedestrians at the crosswalks, we had GP and HOV traffic and heavy trucks. We had there's a freight an at-grade rail crossing here at the 528 interchange. And that was one of the kind of main sources of congestion in Marysville and one of the driving forces behind this project and providing a second access into Marysville was to just reduce congestion for folks getting into Marysville. So that rail crossing was included in our network. We also included public transit, the bus routes that operate in our network. So we were trying to pull together a lot of different elements into one single model. So it was fun and it was also challenging. There's quite a few interchanges that we include in our network, and the adjacent arterial intersections. This model ran for about 5.5 hours. So that was the simulation time. So that's a 30-minute seed, and then we simulated 5 hours. So we had to collect turning movement counts, and we pull together hour-by-hour vehicle inputs and routing decisions based on those counts and freeway mainline and ramp volume data from WashDOT. We did some vehicle occupancy counts to verify the HOV volumes on the freeway. And it may be a little hard to tell, but our network did include northbound and southbound I-5. But our project was just focused on northbound, so that was the focus of our calibration effort was the northbound main line. So we developed desired speed distributions based on the freeway mainline free flow data. We also used posted speed limits for the arterial speed distributions. We used RBCs for all the arterial intersections and the ramp meters. And WashDOT uses a fuzzy logic algorithm to control the metering rates at all the ramp meters. And we looked at the output data from their system, and in the hours that we were concerned with and the locations that we were modeling, those metering rates were fairly consistent throughout the period that we were modeling. So we chose to model static metering rates instead of varying those with a VAP code. Some other things that were kind of interesting just based on the corridors, there's a truck prohibition in the leftmost GP lane on the freeway. There's also a continuous access HOV lane. And so something that we needed to figure out was how to account for that friction between the HOV lane and the GP lane. And in this continuous access HOV facility, people driving in the HOV lane will slow down as there's congestion in the adjacent lane, just because there's uncertainty and always a chance that somebody could weave in front of them. And so when the volume in the HOV lane might be, way below capacity, we still see speeds that drop close to the speeds in the GP lane. So we talked to our friends on WashDOT's I-405 traffic team, and if you're not familiar with that project, they've been building and managing a 40-mile Vissim model for years, and so they're a great resource that we were able to talk to, and they shared some VAP code with us that they've been using to modify the desired speed in the carpool lane based on detectors in the adjacent GP lane. So that was a pretty handy solution there.
How far was your spacing on your detectors?
It was on the order of a mile. Yeah. So here were, I guess, the calibration targets that we were using based on WashDOT's protocol were to get the mainline and ramp volumes within a GEH value of 3, and the speeds on each mainline segment also within 3 miles per hour of the field data. And this chart over here, not sure if everybody's familiar with those, but congestion heat map, something that WashDOT uses on a lot of their projects. So we've got time on the x-axis and location on the y-axis, and then the color bands represent speeds, where green is free flow and black is stop and go. So that was a helpful tool. So these heat maps on the left are from our project, and we can note, the colors don't match up exactly, and what we found was that a lot of our calibration values were right at the threshold of those color bands, like right between the red, black, and yellow color band. So there were some variations there, but we were able to calibrate and meet WashDOT's goals. That was quite challenging. We made global adjustments, so we were replicating measured capacities for the mainline lanes, and then we had kind of local driving behavior adjustments for a lot of the weaving and merging areas. Needed to use a few reduced speed areas where there's some sharp curves on the main line, and then of course adjusting the lane change distance for the connectors near the on and off ramps. But all of that time was well spent because it really did build a lot of confidence in the model. And so when we'd go to stakeholder groups and they would see the outputs and watch videos of the simulation, we had feedback from state trooper that said, yeah, that's really what happens out there. So it was, I feel like that kind of feedback helped our team and also helped as we were modeling alternatives. And so the stakeholders would then have some confidence in what they were seeing in the results and be able to make a recommendation for a preferred alternative based on our input. So this slide shows side-by-side comparison of a lot of all the alternatives that we tested. I think what we see here, there's still a big bottleneck on our network that's generated from the US 2 interchange, and that was not in our project area, not something that we were able to mitigate. So that was something that remained in the future condition, but then we were also able to see as we add the ramps at the interchange, there are some benefits, and then as we add capacity on the main line of northbound I-5, we're seeing a lot of potential to reduce congestion. And the project's recommendation was to go with this build 5. So the plan is to extend the HOV lane that currently ends at US 2 and build that into our project area. So that's what we've got. I'd like to thank a lot of our team members. They provide a lot of input and guidance and assistance on this, so just thank them. And yeah, do we have any questions?
Actually, I have a question. So I noticed that you coded the Z elevations in for a 12-mile corridor. How was that process, and what was your experiences with that?
It wasn't too bad. We used contour data from USGS and made some estimations, but it really wasn't too time-consuming.
Was it something where you coded it manually at each spline point, or automated?
It was not automated. So, yeah, it was a manual process there. But like I said, it wasn't too time-consuming because a lot of the corridor is generally flat. Go ahead.
Yeah, you had explained that you had slower speeds in high occupancy lanes when it was slower in the other lanes. When you analyzed the heat maps, did it include that impact? Were the speeds that you had there ones of the high occupancy lanes only, or also of all of those lanes?
The ones that we showed here were for the GP lanes. Yeah, just the GP lanes. So we had a separate set for the HOV lane.
Thank you.
So I have two questions. First, about the driver's behavior that you said you adjusted it to local conditions. What parameters did you look at and how you did it, like for the field survey? And then the second question is, were there any other criteria other than the speeds that made you pick option number 5 over 3 here? Because like they look kind of the same. I was wondering if there were any other criteria.
Yeah, that's a good question. So when we were looking at the driving behavior parameters, it was mostly CC1. It's the one we changed most often. I'd have to go back and dig through some of it, but we did tweak some other values, mostly following what we had seen from the 405 team, just kind of consistent with another large washed-out project. As far as selecting between these two alternatives, I believe there were some cost considerations as far as where widening would be required, and then WashDOT was considering operating this facility dynamically, so potentially changing between HOV and GP based on time of day, and having signs, electronic signs to manage that. They are also in a budget crunch, so the final decision was just to build a permanent HOV lane, so a static facility.
Thank you.
Thank you, guys.
Presentation.